Okay, so our next speaker is Aleksander Lenart, and he's going to speak about cosmology in the realm of QSOs and GRBs.
Hello, thank you for this nice opportunity to present my research here today. I will take a little bit different path to cosmology, and most of the talks we had were about getting more and more precise, more local data, but I will deal with a noisy data, but at very high redshift. Namely quasars. We observe quasars up to redshift 7.5 and GRBs up to redshift 9.4. And there is a possibility to still extend this range further. So it seems like a really nice tool to discover what's happening in the universe, how the universe evolves with redshift. The research that I will present is an effect of a long few years of work by the people you see now on the screen. We were led mainly by Maria Giovanna Dainotti from the Tokyo University. First, I will start with GRBs. Of course, I will introduce a correlation which enables me to get the luminosity distance and then do some cosmology. But first, before we get to cosmology, I will tell about some issues. I will do only two. There is much more, but I could do a whole conference only about it. And then, we have very few GRB data. So we decided, let's take quasars. They have plenty of data, see what happens. So I will repeat basically everything I did for GRBs, but for quasars. Okay, so to the introduction of the correlation. It turns out that a lot of GRBs have a very distinctive feature. They have the so-called plateau phase. So we can see here the prompt phase, where the burst is the most luminous. Then we have steep decay, and then we have like a flat, calm part of the light curve, after which we again have a steep decay. And the end of this plateau, marked by this red star, seems to be a good way to standardize GRBs, because the time of the end of the plateau and the luminosity at this point are tightly correlated with each other. Dainotti discovered this long years ago already, and then further extended this correlation by addition of the peak luminosity, 1 second peak luminosity, establishing this way a three-dimensional fundamental plane for GRBs. So let's arrive to the first issue. We observed that the fundamental plane fits very good all kinds of GRBs. But we know that we have two distinct classes. We have a long GRBs, which we consider to be a result of the collapsar, while short GRBs emerge due to a merger of neutron stars. And we can divide it even further. The new classes are still emerging. What is important that we found a huge differences between the fundamental planes for all the separate classes, and we found some clusterings in this luminosity, time, luminosity space. So we really need to pick a robust sample. We decided to take the biggest robust sample, which is the long GRBs without supernova observation, and then started to control the data quality. So we choose only the GRBs which had a very flat plateau, did not have any bumps or flares which would break our fitting of the light curve, and we need a good coverage of data at the plateau. This way we got 64 sources establishing the our, as we call it, platinum sample. Here you can see it in 3 dimensions. It's always good to have something moving on your presentation, with intrinsic scatter of 0.34. And now let's dig into another issue. We have to check before we can say that GRBs are standardizable if their properties do not evolve with redshift. But we see here a strong selection effect. We do not observe the faint sources far away. And this can induce an artificial correlation with redshift. So we want to have a real correlation with redshift, and thankfully there is a statistical method for this. So the Efron et Petrosian in 1992 came up with a test statistics which enables you to quantify if the evolution does exist or not. You basically test each point. You take the set in which this point does not have evolving selection, but have a selection parallel to the axis, so it does not induce a correlation, and you count sources. Similarly to Kendall's tau statistics, you count the sources in this associated set, which is not truncated in an evolving way. And if there is no evolution, you expect for this source to have exactly the same number of sources above it and below it. So this way we are establishing the expectation value, this ni plus 1 over 2, and the rank value ri is the number of points either above or below the luminosity of a given point. Then we sum it over every point, so we test for each point if this point feels evolution in its associated set without this curved truncation. So if we get tau equal to 0, it means that there is no evolution. Unfortunately, for GRBs, we got like tau equal to 5. So the tau statistics is normalized. That means it's 5 sigma away from no evolution. So how GRBs can be standardizable now? If we see the real evolution, this is a big trouble, but it was not really my idea, but it's long established in the literature, that we can try to detransform the evolution from our distribution of luminosity. So if you assume that your distribution of luminosity can be described as a multiplication of luminosity function and some function of redshift, then you can transform observed luminosities by dividing by this established function. Okay? So if we assume some functional form of this function, we can use the tau statistics as a fancy fitting method, the selection bias free method to establish the evolved quantities. Here is another animation where you see that exactly here around k equal 2.6, we have tau around 0, so this is our de-evolved solution. Under the assumption that the evolutionary function is 1 plus z to the power of k. This is just the simplest choice you can make. You can make also other choices. You just have to fit some model. So we repeated calculations for all the parameters of the GRBs, and all are strongly evolving. So we have to take this into account. And when we did, thankfully, the correlation still exists. And what is interesting, the intrinsic scatter became a little bit smaller. So it seems that we did discover a really nice correlation. But another issue arises. life is an issue. When you assume some omega m to calculate luminosity to obtain k, right? And you will want to use further this k in cosmological computation, you will deal with circularity problem. Your results, your output will be biased by the first-hand assumed cosmology. So what I did, I computed this evolution over a grid of parameters of omega m. You could do any cosmological parameters, and I also did W and also did omega k. Also, you can vary few cosmological parameters together. We also did that. And it is really important to do this, as we will see later. So once I have this grid, I can interpolate between those points. And now I have numerical function which I can input into my MCMC computation, and I can try to do some cosmology. And for GRBs, we, found a nice fitting. We always have compatibility with lambda CDM. Our platinum sample maximum redshift is around 5. So these are the results up to this redshift. But we find a compatibility, but when we joined supernova and GRBs, turned out that, and the BAOs, it turned out that the results of omega k became less and less compatible with 0. And when we further added quasars, it turned out that the results are even more far from the flat universe. Okay, speaking about quasars, let's check how we did it. Matilda at Tuesday gave us a really nice introduction to the resulity-Luso correlation. This work done by this group is incredible. They really did an amazing job. They proved that this correlation is intrinsic, that it has very low scatter, and the best thing for me probably, it has a lot of sources, 2,421. Even if they did a great job, I think they still neglected this evolution. And yeah, I repeated this, what I did for GRBs. I did apply for the data set, the Efroment-Petrosian method. I found a tremendous incompatibility with no evolution, like tau was equal to 10 or more, I don't really even remember. We again see that the k does depend on omega m. We see very smooth behavior. So once again, I interpolated between the points, got a numerical function, input in MCMC computation, and what are the results? First, if you do a naive fit with raw resulity-Luso data, you get this omega m bluing up towards 1. We saw in Tuesday on one of the plots, if you enable omega m to be anything, it's becoming 2, as it's not really meaningful in the lambda CDM model. When I fixed the correction for evolution, I also got a strange results of omega m smaller than 0.1. Finally, when I applied evolution as a function of omega m, I got a peak around 0.3. We got here only 2 sigma closed contours, but I see this as a very significant improvement, especially that very similar results were obtained independently by Wang in 2022 with the copula method. Okay, we also saw this plot on the left. On Tuesday, we've claimed 4 sigma tension with lambda CDM. this underestimation of distance luminosity is exactly the reason why we get so strange results for omega m when we don't consider evolution. When you do consider evolution, on the other hand, you, in exactly the same beam, you get very contrary behavior. It's now slightly overestimated. But still, this is within 3 sigma with a lambda CDM model. So with this very simple power law evolution, we can fully explain this tension. And this gives us possibility to get finally realistic results with quasars. The thing that in my calculations, that distance at high redshift is overestimated is actually something which is predicted by a F at R model, which was used for example, by Eleonora to alleviate the Hubble tension and sigma tension. So I'm not saying my results clearly points to this modified gravity. We are very far away from this. But this high redshift range seems very important to distinguish between models. I would just like to mention kilonovae because we had a very nice discussion yesterday about their importance. The interesting thing is that the GRBs associated with kilonovae very tightly follow the fundamental plane with a dispersion of 0.21. We have only 8 sources, so this is very few. And that's why the error on this scatter is so high. But I am becoming now very enthusiastic about kilonovae because we will have a very multiple choices of cross-checking them very independently. We will be able to determine distances with gravitational waves. We have this fundamental plane. We also have this model-dependent kilonovae calibration. And possibly there will be more, like the peak correlation of Amati. It holds for most of the GRBs, so I did not test it. But if it would hold for kilonovae as well, we will have quadruple test. This seems really exciting. Thank you.
Thank you, Aleksander. Questions or comments?
Hi, thank you for the talk. So, as personally involved in this thing, it's still not completely clear to me. I have 2 main questions. The first is, you say there is this luminosity evolution. Obviously, you don't have to apply fancy statistics to see that low redshift quasars are less luminous than high redshift quasars, right? But my question would be, if in the flux-flux regime the relation doesn't evolve with redshift, why would you care about the fact that high redshift luminosities are on average higher than low redshift luminosity? Because in principle, if the relation is the same and the slope of the relation doesn't evolve with redshift, and you can test it by using fluxes, I mean, you're looking at 2 different parts of the luminosity plot, but you're fitting the same relation. So it's still not, I also read the paper, but I still don't understand why this would be an issue by itself.
So we are referring to this binning and checking in the bins, the slopes in the fluxes. The point is that with the fluxes, you cannot check slope. Sorry, not slope, normalization. And if you will do this in luminosity, you will see evolution of the slope of the normalization.
The evolution of the normalization in the flux of bin is the Hubble diagram itself, so you expect it to evolve as luminosity distance varies with redshift.
No, you have only one parameter, right, in your correlation.
Yeah, like the beta parameter doesn't evolve, but you cannot test it with luminosities because you have to assume a cosmology, right?
Exactly. And the slope is correlated with normalization, as we see here, right? So if you renormalize beam in flux to 0, in my opinion, you're accidentally fixing the slope.
That correlation that you see there, if you do an MCMC with flux by simply subtracting the mean of the X-ray and UV flux from your data, that disappears because in principle they're not correlated if you fit around the pivot point of the axis.
Yeah, but you have to arbitrarily something subtract, right?
Yeah, which is the mean of the flux points, the flux values that don't depend on any cosmology choice.
They don't depend on the cosmology, yes, but this analysis is like not representative of the whole sample. That's what I'm referring to.
Yeah, because I agree with you that we lack low luminosity objects at high redshift, but
I mean, this is selection, but we lack high luminosity at low redshift. Right?
Oh, as well, yes. But again, I still don't see, if you remove the correlation by subtracting the mean, which is something that you have to do to avoid that shape over there, I don't see what kind of bias is induced by doing that in the flux regime.
I mean, probably we will have to do some big simulation to like study this in depth. But how can you say something about the evolution if you are checking, well, just one parameter into parameter correlation?
Well, for the non-evolution of the beta parameter, I think, because when you cross-correlate with supernovae in the low redshift range, the shape of the Hubble diagram of quasars is the same, matches the one of supernovae. So use supernovae to find the 0 point of the Hubble diagram, but if the beta parameter of the relation would evolve with redshift, this would mean that you would see a change in the shape of the Hubble diagram with quasar compared to the one of supernovae if you fix the 0 point. So at least for when we have supernovae, there is no evidence of an evolution of the beta parameter, and I know it's hard for me to think of something physical that would change quasar physics, but only in one of the two parameters of the relation, and only starting at redshift 1.5. Because that's what you would need to say that the tension.
I mean, the correction for evolution is quite small at redshift 1.5, right? It rises exponentially. It's redshift to the power of something. So that's the thing. The evolution is small at small redshift and becomes significant at high.
So you say that the beta parameter is evolving. Like the gamma parameter is not evolving, but the beta parameter is, and that's why you see the tension.
Yeah.
Okay, but I don't see how, because when you do this luminosity correction, you work in luminosity, and so you talk about like removing the circularity, but you assume a shape for this luminosity evolution that is like
equation. Yeah, I fit lambda CDM, so I assume lambda CDM equation. If you want to fit something else,
so you assume lambda CDM, and at the end you find lambda CDM.
I did not assume omega m equal to 0.3, okay, and I got it. And you assumed the same equation, and you got omega m blowing up towards 1, and even going to 2.
Because if the thing is, okay, if you say the lambda CDM is correct, okay, then you see that quasars are wrong because they give you an omega matter that doesn't make sense. But if you go outside of lambda CDM, you can find something that fits the data. So you cannot use lambda CDM to say that quasars are wrong because they confute lambda CDM. I
cannot use quasars to say that lambda CDM is wrong. That's the whole point of my talk.
No, I said like what you said, from what I understood, you're saying, okay, with different values of omega matter, like quasars give omega matter whatever, so there must be something wrong because this value doesn't make sense. But if the data are at tension with lambda CDM, I would expect the value to not be in concordance with lambda CDM.
So you're referring now to this result with fixed?
In general, I don't see the point of using lambda CDM kind of models. Even change omega matter, but like to test lambda CDM, you do this luminosity evolution that instead has like the lambda CDM paradigm.
I mean, you can fit any model you want. You can compute luminosity with any model you want. To do cosmological computation, you need an equation, right? To do such a fitting, you do need equation.
Yeah, I just think that we can do cosmology with quasars without any cosmological assumptions behind it, apart from the calibration with supernovae. I think it's more robust to calibrate at the 0 point with supernovae and then what comes out of it, instead of thinking of assuming an evolutionary equation and testing it with different parameters and then comparing.
I mean, the Chinese Zhang in this year did this, exactly this, with the copula method, and they got perfectly compatible results with me. They calibrated the quasars with a Gaussian process at a low redshift, and then extrapolated.
How do they calibrate without supernovae?
With Gaussian process. They do use supernova to calibrate quasars. They do use supernova to calibrate quasars, yes. And then when they do have calibration, they do the computation at high redshift. They got exactly omega m is equal 0.3.
Thank you for the nice discussion. So it's time to thank Aleksander again.